Today we are going to talk about the imaginary unit, and so what that's going to involve is a lot of rooting and squaring. So what I am going to talk about right now is just a little bit of a thought process around like the square root of 9. So the square root of 9, hopefully for all of us, are able to identify that it's 3, but it's also negative 3. Let's think why. The square root of 9 is asking what number multiplied by itself gives you 9. So the obvious answer is 3. 3 times 3 is 9. But what about negative 3? Okay, negative 3 is also the square root of positive 9 because negative 3 times negative 3 is positive 9 because a negative times a negative is a positive. Okay, so then we need to think about like what is the square root of negative 9? So what if I take negative 9 and I take the square root of it? And it gives me invalid answer because it doesn't really have, it has a more complex answer than what we have. And what we're going to find out is that this is going to involve the imaginary unit. Okay, that this is kind of the question that we're answering today is like what is the square root of negative 9? Because let's think about it. Like 3 times 3 is positive 9. Negative 3 times negative 3 is positive 9. So neither one of those could be it. So a lot of people will say, well, what about 3 times negative 3? Well, those are not the same numbers, so that's not finding the square root of it. So that just doesn't really answer our question. Yes, does that equal negative 9? Yes. But does that answer what the square root of negative 9 is? It does not. Okay, so let's get started on today's lesson. Okay, 4.4 is going to be all about the imaginary unit. We are going to have two learning targets. One, they're going to be able to simplify square roots. Okay, and then another one that says you're going to be able to define, add, subtract, multiply, divide complex numbers. And that you can also find complex solutions and zeros. Okay, so basically what we're going to have here is going to be called the imaginary unit, and it's going to be referred to as I. Okay, and it's defined as that if I square I, so I take I squared, it's equal to negative 1. Okay, so then that means it can be written that I can be used to write the square root of negative 1. So if we think about it in this, like if I wanted to get the I by itself, isolate the I could take the square root of each side. That's how you would undo squaring, because squaring is undone by square rooting. And so then, my squaring and square rooting cancel each other out to refer that I is equal to the square root of negative 1. Okay? And I is a complex number. Okay? And it can be written in standard form if the number is written in the form a plus or minus bi, where a and b are real numbers, referring to that a and b are like the numbers that you've seen and dealt with essentially your whole life. Okay? So if b is not equal to 0, okay, then that means that a is just an imaginary number. Okay, so it's a complex imaginary number. And then if a is equal to 0, okay, meaning that it's just the form bi, and then b doesn't equal 0, then it's a purely imaginary number. And again, it can be determined that I is equal to the square root of negative 1. Okay, this is the biggest thing that you're going to need to know. Okay, it does have a few properties of finding the square root of a negative number. Okay, if n is a positive real number, okay, then the square root of negative n is essentially you'd pull out that negative 1 to get I square roots of n. Okay, and then using the first property here, that if you were to square this here, okay, I squared, well, we already know that's negative 1. And then the square root of n squared, those would cancel each other out just to become n, so negative 1 times n, which is the opposite of n. Here's just some examples of that. Okay, let's go ahead and split these up, or simplify some square roots. Okay, and so essentially what we want to do is we just want to break these up into little parts that I know I'm going to be able to do. For example, the square root of negative 25, I just want to split this up into just all sorts of perfect squares. So first I'm going to have like the square root of negative 1 times 25, right? I'm just splitting it up into two nice, neat, perfect squares that I have. Okay, so negative 1 times 25 is negative 25. Okay, and I'm splitting it up with negative 1 and 25 because I know now that the square root of negative 1 is I. Okay, so now I can go ahead and, even here I can rearrange it to go 25 times negative 1. So, and then here I can split this up into the square root of 25 times the square root of negative 1. This is how square roots work, right? If they're multiplying each other, then I can multiply the individual square roots of each other. Okay, so what is the square root of 5 or 25? Well, for us, we're finding the principal square root, essentially meaning that we're only finding the positive square root. We are going to say that this is just 5. Okay, and then here we have the square root of negative 1, which is just I by definition. So the principal square root of negative 25 is 5I. Okay, so let's move on to 2. 2 is going to say the square root of negative 72. Now this one here is a little more complicated because 72 is not a perfect square. So what I want to do is I want to find all the perfect squares, okay? I'm going to do my perfects here, and then I'm going to do my non-perfects here, okay? So what I'm going to do is I'm going to split 72 up into a perfect square times a non-perfect square. So for example here, I'm going to go, we have to think about what square root, what perfect square is going to divide into 72 evenly. So here it might be helpful to get that sheet out that we dealt with at the beginning of last class. Okay, and we can just start listing through our perfect squares, right? Okay, so, like 4 or 9 might divide into that, but really we're looking for the largest one here, which is 36. 36 divides into 72 exactly 2 times. So I can say that this is 36 times negative 1. Okay, and then what's left over? When I divide negative 72 by 36 and negative 1, there's just a 2 left over. Okay, and 2 is a non-perfect square, so I'm putting it into that non-perfect square category. Okay, so now I look at this, and now I can split up. What's the square root of 36? 6. What's the square root of negative 1? It's I. What's the square root of 2? Well, that isn't a perfect square, so we're just going to write it as square root of 2. Okay, so the principal square root of negative 72 is 6I square roots of 2. Okay, so let's go ahead and do 3. All right, so now I'm looking at this one here, and I'm trying to identify our, well, this is 9 is a perfect square, so that means negative 9 is going to be a nice, neat, perfect square as well. Okay, so I can rewrite this as negative 5 times the square root of 9 times the square root of negative 1. Okay, I don't have to split this one into perfect squares and non-perfect squares because 9 is itself a perfect square. Okay, so this is going to be negative 5 times 3 times I. Okay, so then I could just multiply this all together. Negative 5 times 3 is negative 15 times I, which is negative 15I. All right. So that's a learning target itself, which is simplifying square roots. Let's go ahead and see if we can try A, B, and C on our own. Okay, I'm assuming that you've already paused the video and tried these on by yourself. So I'm assuming that you went and split up this into the square root of 4 times the square root of negative 1. Square root of 4 is 2. Square root of negative 1 is I. Okay, in B, you're looking for, this is a non-perfect square. Okay, so you're looking to split this up into perfect squares, which would be 4 and negative 1, times non-perfect squares, so perfect squares and non-perfect squares, which would end up being 3. Okay, where do these numbers come from? 4 times negative 1 is negative 4. Negative 4 times 3 is negative 12. So I'm just decomposing negative 12 into 4 times negative 1 times 3. Okay, and I'm choosing specifically this because this is the largest largest perfect square that divides into 12. Okay, meaning that I can split this now up into square root of 4 times square root of negative 1 times square root of 3. Square root of 4 is 2. Square root of negative 1 is I. And then square root of 3 is just square root of 3 as that is an irrational number. So we're just going to write it in the most simplified form. Okay, and C. We're going to go ahead and try this one here. Now, 54 is not a perfect square, so I need to find perfect squares and non-perfect squares. So we know negative 1 is going to be one of them. We just got to figure out what that other number is going to be. 9. So 9 times 6. Okay, 9 times 6 is 54. Okay, so now that I have my perfect squares, I can go ahead and just rewrite that a little bit here and say this 2 times square root of 9 times square root of negative 1 times square root of 6. So this is going to be 2 times 3 times negative, not negative 1, I, times the square root of 6, meaning 2 times 3 is 6. So this is going to be 6i square roots of 6. Okay, almost wrote negative 1 there, but it is I. Square root of negative 1 is I. Okay. All right, so now what we can do is we can simplify just some very basic expressions here by like adding and subtracting our complex numbers. Okay, so here if I want to, add these parts together, if there's no multiplication to do, like 4 minus I is a complex number, and then I'm adding to it the complex number 3 plus 2I. Like when I'm just adding and subtracting, you really only have to be careful when you're subtracting the second part. When you're just adding, you can be pretty loose about the parentheses, and you can essentially just combine like terms. Okay, so I need to think, is there anything I need to do to drop these parentheses? Well, when I'm adding two numbers, no, there's not really. So I can just say that this is 4 minus I plus 3 plus 2I. Okay, and then essentially it's combining like terms. I can combine 4 and 3 together. 4 and 3 combine together into 7. Okay, and then I can combine 2I and that negative I into positive 1I. Okay, these are, referring back to like terms. These are non-like terms, so this means the complex number 7 plus I is my answer when I add 4 minus I plus 3 plus 2I. Okay, again, you have to be careful about what the order in which we're subtracting this entire number here. We're subtracting the entire negative 2 minus 2I. So I do need to do some work to drop my parentheses. Now the first set I can just bring down. There's not really much happening to it, but I am subtracting all parts of this complex number. Meaning I'm subtracting negative 2, which is adding 2, and I'm subtracting negative 2I, which is adding 2I. And then now I can go ahead and combine my like terms. 14 and 2 is 16. Negative 2I and positive 2I. Well, those are opposites, and we already know what happens to opposites when I add them together. Well, they cancel out, meaning that this is just the number 16. Okay, so this one's a little more complex, number 6, is that I have a little bit more going on. So again, I need to do some work to drop this parentheses. Sometimes when you're adding here, honestly, you really aren't going to do a whole lot to need to drop those parentheses. Here I'm subtracting the entire number, 8 minus 11I. So that means I have to do some work since I'm subtracting this whole thing to drop the parentheses. So here I'm subtracting a positive 8, so that's just minus 8. And here I'm subtracting a negative 11, and that's the same as adding 11I. Okay, and then now I can combine my like terms. Okay, negative 1 and negative 8 is negative 9. 11i and 5i combined to 16i. So this expression is equal to the number, the complex number, negative 9 plus 16i. Okay, I think now's a good time to pause the video, try D, E, and F on your own, and check it with me when you are done. So I'm assuming that you've already done that. Okay, and so now we are going to go ahead and check our work. Okay, so D, we have to think about whether there's much work needed to be done to drop the parentheses. In this situation, there is none. We can add two numbers in any order we want, and it doesn't change the value specifically of the second number. So here we're just going to go 2 plus 4i plus 3 minus 3i. So now I can combine my parts, like 2 and 3, into 5. And then I can combine 4i and negative 3i into I. So these two complex numbers add into the complex number 5 plus I. E does have some work required to subtract or drop these parentheses. Okay, so the first one, though, it's kind of a freebie. I get to leave those. But then I have to subtract this entire second. So I'm subtracting 3 and I'm subtracting negative 5i. So subtracting 3 and subtracting negative 5i would be the same as adding 5i. Okay, and so then now I can combine parts that are alike, such as 21 and negative 3 to get to 18. And then 4i and 5i would combine into 9i. Okay, last, F. Here I do have some work I need to do because I'm subtracting the number 1 minus 6i. So I have to think about what it looks like to subtract each part. So I'm going to go forward and I'm minusing a positive 1, so minus 1. And then I'm going to minus a negative 6i, which is the same as adding 6i. Okay, and then I can combine 4 and minus 1 into 3. And then I can combine 6i and 4i into 10i. Okay. So that is part of a learning target. The entire learning target itself is actually is adding, subtracting, and multiplying as well. Okay, so this is just part of the learning target. There's some more layers that we have to add to it. Specifically, multiplying. Now, there is one big fact that you need to know, is that I squared is equal to negative 1, okay? So this allows us to simplify our answers down extremely you should really never have an I with an exponent larger than 1, because we should be able to always just keep simplifying it down until you get your answer reduced into just a general complex number. So let's go ahead and look at what that looks like. So here I'm multiplying. So I'm going to have to, right here, I have to distribute. So I'm going to have 6i times negative 2 and 6i times a positive I. So 6i times negative 2 is negative 12i. And then 6i times I would be 6i squared. Okay. But again, we have this fact now that I squared is equal to negative 1. So I can go ahead and I can rewrite this number. But instead of I squared, I'm going to have negative 1. Okay, which simplifies into negative 12i minus 6, because 6 times negative 1 is negative 6. And then lastly, I want my final answer in A plus or minus BI. So that means I can just rearrange this into negative 6 minus 12i. Okay, now we can move on to 8. 8, we're multiplying two binomials. So for us in my class, I would prefer to use the box method. Okay, so we're going to have 4 minus 2i, 5 plus 3i. And we can go ahead and multiply. 5 times 4 is 20. 5 times negative 2i is negative 10i. 3i times 4 is 12i. And then 3i times negative 2i is negative 6i squared. Okay, so then I'm going to go ahead and we can combine these two parts together into a positive 2i. So I get 20 plus 2i minus 6i squared. But again, I know the value of I squared. So this is going to be 20 plus 2i minus 6 times negative 1. Okay, so now I can multiply negative 6 times negative 1. Okay, they're going to multiply together to positive 6. And then lastly, I have terms that are alike, such as 6 and 20. Okay, so this is going to end up being 26 plus 2i. So again, you're seeing that even though I might end up with a I with a variable or with an exponent, whatever that is, somehow it's always going to reduce down either to, negative 1 or some version of I, like whether it's negative I or not. Okay. All right, so I think right now is a fantastic time to try G and H on your own and then check it with me here in a moment, which that moment is right now. Okay, so I'm assuming you've already tried here, so you're going to distribute 3i to each of these. Okay, so you're going to get 12i plus 6i squared. Well, the value of I squared is negative 1. So this turns into 12i minus 6. And then I can rearrange this to put it in our standard form, negative 6 plus 12i. Okay, the last one is two binomials multiplied by each other, so we're going to use the box method. Five minus 3i, 2 minus 8i. Okay, so then we're going to just multiply each here, so 2 times 5 is 10, and 2 times negative 3i is negative 6i. Okay, then we have 5 times negative 8, which is negative 40i. And then negative 8i times negative 3i, so negative times negative is going to be positive, 24i squared. Okay, so this is 10 minus 46i plus 24i squared. All right. So here our negative 40 and our negative 6i here are going to combine into negative 46. So then I get 10 minus 46i plus 24 times negative 1. So this is going to be 10 minus 46i minus 24, which means we have terms that I can combine together. That's going to be negative 14. So this is negative 14 minus 46. All right. Okay. So essentially all we've done so far is we have just kind of figured out how to use and manipulate I as a number using only the rule I squared is equal to negative 1. And then knowing that I squared is equal to negative 1, we've been able to use all sorts. We've been able to take square roots of negative numbers. That's kind of the biggest thing that we should do. Although you should be able to know how to manipulate it within expressions, the biggest thing is knowing that its biggest use is knowing that we have a way to take square roots of negative numbers. Okay? So what I would like to do is I would like to just kind of talk about this first problem, like conceptually, and then try to figure out what the meaning of our solution is going to be. So if I have x squared plus 9, this is going to be a parabola opening upwards based on what we did in the our third chapter at 9. And I want to know when it's equal to 0. So essentially it's saying, like, when is its y value 0? Well, as we learned in the last section, that's just where it's going to be crossing the x-axis, is really what it is we're just trying to figure out, like, what x values cause me to cross the x-axis. Well, as you can see here, this graph doesn't cross the x-axis and never will cross the x-axis. It's still going to open up. This is where we can get our complex answers. Okay, this is where we are going to have solutions to an equation that otherwise wouldn't. So let's go ahead and see what this looks like. So kind of our rule of thumb here is, set it equal to 0 and factor. Okay, but this is not a difference of squares. So let's try to get the x variable by itself. So then we can square root it. Okay, so let's subtract 9 from each side to get x squared is equal to -9. Okay, and so then here, how would I undo squaring? We would all hopefully be able to tell us at this point, you want to square root each side. Okay, so then here you get x is equal to the square root of -9. Okay, now for these problems, in the past you would take your calculator out, you'd go square root of -9. This problem can't be solved. Well, now we have solutions. It's just those solutions are complex. So we actually can simplify this here. Okay, now the big difference between simplifying the square roots we did before and the ones in actual problems is that it's a positive and negative 3i. So I understand that in previous problems, we would just say that the principal square root is 5i. Because that means we're just looking for the principal square root is essentially the positive square root only. Where in the problems that we're doing now, they're not asking for like the principal solution. They just want solutions. So we need to know that when I square root a number, I'm going to get a positive and a negative version. Okay, so here is our answer. It's positive and negative 3i. Okay, so in this problem here, I'm looking at this, and again, if I add 31 over here, 24, and then I could divide by 3 to get, this problem here, even if I add 31 over here, I don't think it's going to be factorable. So again, let's just go ahead. We only have an x squared, and when you only have x squared, it's totally fine to take this approach of just get the x squared isolated. So let's go ahead and do that. We're going to add 7. Okay, and so we're going to get 3x squared is equal to negative 24. Okay, and then I can still get the x squared by itself by dividing by 3. So I get x squared is equal to -8. So then again, I need to think about like, what can I do to get the x variable by itself? Okay, x squared, I would undo that with square rooting. Okay. All right, and so then now I get x is equal to the square root of -8, which I can split that into perfect squares and non-perfect squares. Okay. All right, so this is going to be x is equal to plus or minus 2i square roots of 2. And again, these are types of problems that otherwise wouldn't have had solutions, but now have solutions just based on us introducing this concept that this I squared is equal to -1. Okay, and then this is our solution right here, plus or minus 2i square roots of 2. Okay. All right. Good time to pause the video, try I and J on your own, and check in with me when you're done. Okay. So I'm assuming you've already done this, so we're going to subtract 32 from each side to get x squared is equal to -32. Then you square root each side to get the x variable by itself. To find that x is equal to, okay, this is a non-perfect square, so we're going to have to split this up into perfect squares times non-perfect squares. The largest perfect square that divides into 32 is 16. Okay, so then we can split this up and say that this is x is equal to plus or minus 4i square roots of 2. Then we can subtract 33 on this one. We're just trying to get x squared by itself. To get 5x squared is equal to negative 30. Then we're going to divide by 5. X squared is equal to negative 6. Then I square root each side. Okay, and then we get x is equal to, well, there is a perfect square that divides into negative 6, and it just happens to be negative 1. Otherwise, 6 has no other perfect squares that divide into it, meaning that, you know, the perfect square here that divides out is I plus or minus I square roots of 6. Okay. So let's move on to 11 and 12, which the positive part about 11 and 12, folks, is that it's asking for zeros. So when it's asking for zeros, it's essentially asking for when does the graph cross the x-axis. When does it cross the x-axis? But a lot of times in problems that we've already seen, they don't cross the x-axis, but that does not mean that we cannot find solutions to it. Okay, we can still find x values that make the function equal to 0, which means that's where it would cross the x-axis, even though it's not. So again, we're just looking for x values that are going to make this equal to 0. So that what this means is I need to set this function equal to 0. Okay? And then I can solve the exact same way that I did above. Okay, so I can subtract 20. You know, I only have an x squared term, meaning I could just try to get that term by itself, so I can square root. Okay, so all this other algebra, I'm assuming we have down. Okay, and then I take the square root of it. The square root of x squared is x. The square root of negative 5 is plus or minus I square roots of 5. Okay, because the square root of negative 5 splits up into square root of negative 1 times square root of 5. All right, and then lastly, again, we're just trying to find the zeros, meaning we're trying to find the x value that makes this whole thing 0, so we can go ahead and do that. All right, and so then I'm going to add 96 here. Get 96 is equal to negative 8x squared. And nope, this is positive. And then divide by negative 8. Oh, let's go ahead and use calculator. I'm not 100% sure what that is. 96. Okay, so it's 12. All right, so we're going to say that this is negative 12 is equal to x squared. And then we have to take the square root of negative 12 is equal to the square root of x squared. All right, and so then we can go ahead and determine, we have to break this up into perfect squares and non-perfect squares. So this would be 4 times negative 1 times the square root of 3. Okay, because square rooting and squaring undo each other. Okay, these numbers all multiply to negative 12. This is the largest perfect square that divides evenly out of it. So this would give me plus or minus 2I square roots of 3 is equal to x. Okay. Good opportunity to go ahead and solve K and L on your own. And when you are done, check it with me. Okay. So we have K. Again, we're just finding the 0, so we're finding when it is equal to 0, the x values that will make the function equal to 0. So I'm going to start by adding 18 to each side to get 18 is equal to negative 2x squared. Then I would need to divide by negative 2. Negative 9 is equal to x squared. Lastly, I need to square root each side. Okay, Well, we know that negative 9 is a perfect square. Its result is going to be 3i, so my answer is plus or minus 3i. Okay. All right, letter L. Again, we're just finding when it's equal to 0. Okay, so I'm still looking for the x values that make this equal to 0. And we're going to subtract 35. Negative 35 is equal to 5x squared. Then divide by 5, then divide by 5. It's equal to x squared. Then I need to take the square root of each side. Okay, these are going to cancel just to x. And this here, the only perfect square there is negative 1. So we're going to have negative 1 times square root of 7 to get plus or minus I square roots of 7. Okay. There's one thing that I would like to do before we end this lesson here today. And if I can get my sheet of paper. Okay. I would just like to take letter K's answer. Okay, I would like to take the answer to letter K. So we have f of x is equal to negative 2x squared minus 18. And I would like to prove to you, even though this is a complex solution, I would like to prove to you that this is indeed a solution. Okay. So we believe that x is equal to plus or minus 3i. Okay, so what I'm going to do first is I'm going to test f of positive 3i. Okay, so that means I'm going to go negative 2. Let me go ahead and pull this off to the side. Okay, I'm going to have negative 2 times 3i squared minus 18. Okay, so then I need to go negative 2 times, well, here we would have to square each of these numbers. So 3 squared is 9, and I squared is negative 1. Okay, 3i squared. So technically there is a little intermediate step here, so let's go ahead and write that. Let's go negative 2 times 9 times I squared, right? 3 squared is 9, I squared is I squared. Okay, but we know I squared is negative 1. Okay, so negative 2 times 9 is negative 18 times negative 1 is 18. So we get 18 minus 18, and that's equal to 0. So this is indeed the x value that makes this equal to 0. But that's just the positive version of this. Let's explore the negative version. So the negative version is finding f of negative 3i. So then I get negative 2 times negative 3i squared minus 18. So here I get negative 2 times, well, negative 3 squared, negative 3 times negative 3 is positive 9. And I times I is I squared. Okay, and so then I get negative 2 times 9 times, well, negative 1, because that's what I squared is equal to, 18. So then we get negative 2 times 9 is negative 18. Negative 18 times negative 1 is positive 18. So again, this is equal to 0. So that was just me showing you that these answers, though, just based on the rule set that we put in place, that I squared is negative 1, it allows us to have solutions to equations, specifically quadratic equations, that otherwise wouldn't have had a solution at all. Okay, and that's really the biggest function of I and its complex solutions, quite literally. Okay, otherwise, go ahead and move on to the homework, and I will see you at the beginning of the next section, 4.1.